Sticky once you have DB browser and have downloaded the zip file from this setup, which is up here at the top. And make sure to open this page up, and then you'll see download all.
Oh, I download all of them.
Mm-hmm.
Yeah.
And this will download it as a zip file.
Yes.
Get the zip file into a new working directory, and then I'll show you how to actually open stuff in the.
No, actually, I did download it just as files.
You download as files?
Yeah, it came out like this. So
Okay, that works too. And Macs often like automatically do that stuff with zip files. So.
What is the file that we're working on?
Well, a bunch of them.
A bunch of them?
Yeah, we're kind of talk about how you can take CSVs and put them into a database like this. And then let me grab this. So once you have them, throw up the green sticky. It should take a little bit to grab.
I'm supposed to download the software too, the DB.
Mm-hmm. And while this is going, I'll kind of talk a little bit about what we're actually doing here. So SQL allows us to work with what's called a relational database. I'm going to talk about what those are. I'm going to talk about what SQL is. It's structured query language. I'm going to talk about why they're useful, and we're going to actually create a database from CSVs. So we're going to start with CSVs and create a database using this. This is already populated, but we're going to create a new one in a moment. And then we're going to talk about data types, which is something we haven't talked about too much. We've talked about a little bit, but we're going to talk about all the different data types in SQL, because SQL is very strict about its data types. We're going to talk about select, group, adding, and analyzing subsets of data, and then we're going to combine data across multiple tables. So to start, let's talk about kind of where we are in a project's workflow. So we used Excel and OpenRefine to go from messy human-created data to cleaned computer-readable data. And so now we're going to move to kind of the next piece of the data workflow. We did R in between, but you can kind of do both at the same time.
Okay.
So we're going to move, and this is how we get files to a database, and then we can draw the database into R. So SQL stands for Structured Query Language, and it allows us to interact with relational databases through queries. These queries can allow you to perform a number of actions such as insert, update, and delete information in a database. And so the data that we're going to be using is a time series for a mammal community in southern Arizona. And so this this project was running for 40 years. And this is a real data set. If you feel like seeing what a real data set looks like and understanding why we start with these subsets, I'm going to drop a link to that at 3:32, which I wouldn't look at right now because it's really overwhelming. But it kind of makes the point of why we use these programmatic tools and don't just do things by hand anymore. So the first thing that we're going to do is we've downloaded that portal project data set, and we're going to look at 3 files. We're going to look at surveys, which is down here. Click. We're going to look at species.csv, and then we're going to look at plots.csv. And the first thing I always do when I look at a file is I look at the size of the file. So 997.6 kilobytes, that's about a megabyte, which is a lot of text data. Species is 1.6 kilobytes, that's really small, quite a bit smaller. And then plots is 539 bytes. Which is, to open that up, you can see that's So if you think of like each character as a byte, you can sort of look at the size of a file and know how much data is going to be in that file. I know that may seem like pedantic and boring to even say that, but so yeah, so we're going to just look at them and look at what they have. So we have plots, which I'm going to open them in text because I like that more.
Do we need to create the new database before that, or how you can access to the file?
You downloaded the zip file, the 1314459, and these comma separated value tables are going to be inside that zip file.
Oh, yeah. I thought like we already opened it with the DB browser.
Not yet.
Not yet.
We're doing the initial stage of where we have these data files, and
You want us to open it in text better?
I mean, or you can look at it up here if you don't feel like it, or open it in whatever you are more comfortable with. I'm most comfortable looking at things like this and then getting into a spreadsheet later, because this gives me like a sense of exactly what data is there on the disk, right? Like this is like the closest representation of like what's like really there. And so we look here and we can know that in surveys.csv we have record ID, month, day, year, plot ID, species ID, sex, hindfoot, length, and weight. And we have a whole mess of records. Since we have record IDs, you can see that those are counting up.
None of them has weight, right?
Hmm?
None of them has weight
Mm-hmm.
added.
Yeah, you can see sometimes those trailing comma. And it's just, I guess, they had a scale or didn't have a scale. And that's going to be often the case. We're going to have data sets that are incomplete. So yeah, now that's kind of what's in that file. That's the fields in that file. So what if we had to ask these questions? How is the hindfoot length and weight of the Dipodomys species changed over time? What is the average weight of each species per year? And what information can I learn about Dipodomys species in the 2000s over time? What would I need to answer these questions? What files have the data that I need? And what operations would I need to perform if I were doing these analyses by hand? Like, what would we have to do if we had to answer the question? We'll start with this first one. How has the hindfoot length and weight of Dipodomys species changed over time? Like, what would we have to do to answer that question with this data set? And so, to sort of like break it down to very specific, in order to answer these questions, what we need to do is do basic data operations, which we've already done some of with R, where we took subsets of the data, took rows and columns. We did grouping in there as well. And then also do some math and other calculations on that in order to get an answer, like averages or medians or sums. And we would need to combine data across spreadsheets. Like if we wanted to find the average weight of each species, we'd have to look at this data in order to get something that, like, especially when you think about when you go to someone, you don't want to hand them CM35, CS42. Like, that wouldn't make any sense to somebody. I mean, it might if they had all that memorized, but who would? You want to have the genus and species listing, and then average weight is 36. And that's the sort of stuff that SQL is good for. And we don't want to do that manually. We want to use this tool. And this tool is a relational database. And so like any other tabular data, we have data tables. But what makes relational tables different from the data frames and the Excel spreadsheets that we were looking at before is that you can link them together based on some sort of key in between them. And so they generally have a unique key. So if you look at the plots.csv, there's this plot ID. There's 1, 1, 1, 2, and 1, 3, etc. And so that is the unique key for this table. And it's the same with species.csv. Each one of those species codes, well, species IDs, is a unique identifier for this table. And then those plots and species relate to, if you look at plot ID, which is the 1, 2, 3, 4, this here, and then species ID here, these tables relate to this larger table. And so relational databases have some advantages. It keeps the data separate from any analysis. There's no risk of accidentally changing your data when you analyze it. If someone else is, say, adding records to your study, you just press return again on your query and you get the updated results. So relational databases can be worked on at the same time. These are very fast for large amounts of data. This is what probably 90% of the internet runs on SQL queries. I mean, this is what pretty much the whole world runs on databases like this. And it improves quality control of data entry because there's strong type constraints. And then people working on these often use, say, Access, FileMaker, Oracle application, and the forms that they have make it very simple for people doing data entry. Like they can just get into that data entry flow, which is, if anyone's done data entry for a job, you know how that can be. You just kind of start entering data. The concepts of these relational databases are core to understanding how to do similar things using programming languages such as R or Python, and we already talked about that. All of these programming, like the people who, like Hadley, who coded the libraries we were working with earlier today, like he knows SQL, and he used some of these ideas from SQL to inspire him to add those functionalities to R. Which is why the tidyverse is so nice. It draws from all of these different sort of modes or ways of thinking about the code. So there's a whole bunch of different database management systems. We're going to be using, and I'm going to throw these away, and we should open up SQLite now, which I'm going to close this and reopen it. Let's see if it does it. Okay. Okay, so you should see something that pops up like this, I guess. And it should look something like this. And you'll have all these tabs. But I just turn all those off, because we don't really need to be looking at the log. We don't need to be looking at any plots right now. We don't need to be looking at the database schema or edit database cell. We don't need any of that right now. And turn off the remote. And then we have this. We don't even really need the toolbar, but you can leave it. That's fine. And so we're going to have something that looks like this. We're going to have 4 tabs: database structure, the browse interface, edit pragmas, which I don't think we're ever going to touch, and then we're going to have execute SQL. This is going to be where we're going to be in most of the time today. And this is where we actually enter in SQL statements, run them, and get the query responses. So that's kind of the straightforward first SQL query. Which I'll explain in a moment, which is select everything from the species table. So we have this database structure. You can see we have 3 tables, which are those CSV files we're looking at. We have plots, we have species, and we have surveys. And then if you click the little triangles and drop down, you can see each of the fields in there. And so if you look, every single one of those fields has a type. And there's a bunch of different kinds of types. So we have day here, which is a big int. What is that? Huh? Big integer. And then we have text, which is text. And then we have floats, which are floating point, which those have the possibility of having decimal places. And they're encoded kind of like scientific notation, but in binary. So they're not necessarily precise. Integers are always precise. Floats can have a little wiggle room, depending on how they're implemented. So what we're going to do, before we do anything else, we're going to open up a new database. And so we're not going to edit table definition, so go ahead and cancel that. But then go to File, and then Import Table from CSV file. And we're going to import surveys.csv. So you can rename it if you feel like it. You want to make sure because the first row does have column headings, check the appropriate box. And then, as we talked about, we can use different import from different field separators, and also different quotation characters, because some data uses double quotes, some uses single quotes. And then we import. So now we have a surveys table imported. And then set the data types based on what you think they should be. And then do the same for plots and species, and put up a green sticky when you're done. Now the table definition is if you're making something sort of actually in the program by hand. Mm-hmm. This is my first time using this software, because since the last time I taught this, they added this, but this is already way better. The last thing was like a Firefox extension that did SQL browsing, and so.
The one you imported was a surveys CSV, right?
Mm-hmm. But after you do surveys, then also need to do plots and species. So once you get it input, you can kind of look at the Browse tab. And I'm double clicking on the lines in between each column. And that is often a way to sort of auto-fit column sizes. So I put up on the board here a list of all these different data types. And we're only using a few of them in this, but there are a lot of different data types that are actually available. And then what's like really fun is that every single implementation of SQL, because there's Access, which is Microsoft's, There's SQL Server, there's Oracle, there's MySQL, and PostgreSQL. And they're all a little bit different. And so have fun. Like Access has text, which is only for up to 256 characters. That's the tweet-sized things, and then the memos are up to 65K plus, and that can be large expandable. And so you have to plan out like an Access database in a different way depending on what kind of text is going into a certain box. But you don't have to worry about that on any of the others. You don't really need to memorize that. I put a link to that at the bottom of the Etherpad. If you tried to import that data, it would probably throw an error. I mean, let's see. So we have this, and we can try to add a new record, right? So 35550. Is that right? And then let's do month 12, day 31, and let's do 2002. Plot ID 3, species ID. Let's do that DM mouse. Male, hind foot length. Wait, those are. I'm going to do plot ID 3.5. How about that? Yeah, it's working in here. It shouldn't. This software may not have strict type checking built in, which it really should. So yeah, normally that would throw some kind of error. Like it would say type mismatch, like only integers. But apparently this software doesn't have that built in, which I guess is fine. Yeah. Thank you. I love finding weird stuff like that, because that is very weird. Does everyone have the database imported and good to go? All right. So we don't want to point and click on this stuff. We can filter things in here, but that's not what we're here to learn about. So go over to execute SQL. And I'm going to make my text even bigger. Let's go 24. So let's start by looking at the surveys table. That's the big one that we have. That's data on every little rat that was captured at that site. When, where, etc. Y'all know this data. So we're going to do select. And I'm actually going to be good SQL style here. It's capitalize, select, lowercase year, from surveys. And then close it off with a semicolon. And so that gives us, looking at the bottom, we got all 35,549 rows. But we only got that 1 year column returned. So SQL does not care about capitalization, but the people reading your SQL do. And this is what they will expect. So just looking at the year isn't too much information, so let's add a couple more columns to this query. Year, month, day. Oh, and control return, control enter will run the query if I didn't say that. Or we can say, you know what, I'm just going to run all. I want every single column. And use that asterisk, the wild card. So like we were doing before, with R, we're using that head function. Here instead, we select everything from surveys and limit 10. And so we can also do something like selecting, let's say, unique values. So we want to know what species have we found. So select distinct species ID from surveys. So we got 49 rows. That means we've sampled 49 different species, and there's a list of their code. And then if we select more than one column under distinct, we get unique pairs of values. So here we get 535 rows. And so we can also do calculations with the values in a query. So if we wanted to look at the mass of each individual on different dates, but we needed it in kilograms instead of grams, so select year, month, day, and then weight divided by 1,000 from surveys. So what's wrong with this query? I'm scrolling through this data. Yeah. So in order to tell SQL, hey, really, we really want you to do this properly, we want to do that 1,000.0. And this is where the typing comes in. Because it ends up coercing it to integers rather than leaving it as floating points. But like, some of those values are kind of long on our scales, and we know that our scales aren't actually that precise. Because like maybe we have cheap scales. So we can round that to 2 decimal places. And this works a lot like the functions that we were using in R. So now write a query that returns year, month, day, species ID, and the weight in milligrams. And then throw up a green sticky when you got it. The weight in milligrams. That's all right, we're Americans. We have.
I can't Google it. It's
We have.
embarrassing right now. If I was still sitting back there, I would have been Googling.
The stickies.
So milli is the.
Is the other, is dividing.
It's.
It's the smaller.
Yeah.
Yeah.
Yeah, our education system confuses us with imperial measurements instead. Instead of the much superior SI. So you see like in this display it's down here. I was going to save this till later, but then we do like as weight in kg. And then it'll change it on out. But So I see a few green stickies, no red stickies.
Oh,
That's how I know when everyone's done.
I tried to give like a subtle look and
it's funny 'cause she's looking at me like, okay,
Okay.
yeah.
Okay, now I see the sea of green that I need. So continue. So let's do select, day, month, month, year, species, ID, weight, times 1,000 to get to milligrams. And then from surveys. So cool. So databases can also filter data. So we can make sure to select only data that meets certain criteria. So let's do another select. Let's select everything from surveys where the species ID equals DM. So that should get us about 10,596 rows. So we can do the same thing with numbers. So we can do select from surveys, and then just kind of right over that, where a year is greater than or equal to 2,000. So everything since the year 2000, we got 5,391. And if we and here's where if we'd use the text data type for the year in our database structure, that would not have worked properly. So we can also use more sophisticated conditions by combining tests with and or. So for example, suppose we want the data on the DM mouse starting in the year 2000. So we do put this in parentheses, the year equals 2000, greater than equal to 2000, and then add species ID equals DM. So that gets us 847 rows. And so if we wanted to get information on all of these D mice, so we use OR statements. Species ID, what is it, DO? And I missed a quote there. So I need to go back and fix it before I run it so that I don't make silly mistakes in front of everybody today. Awesome. 16,127 rows. I'm going to drop this one. This is what we're going to do now. I'm going to drop this one into a text file and put it up here. Can everyone read that? Well, let me put a carriage return. That is what we're going to do now. We're going to produce a table listing the data for all of the individuals in plot 1 that weighed more than 75 grams. And it's going to tell us the date, the species ID code, and the weight in kilograms. So we want the day, month, year, species ID, and then weight divided by 1,000.0. And then we want that from surveys, And then, and so we want the plot ID. It doesn't matter. The weight is greater than 75.
But it has to be in parentheses though.
It doesn't have to be. It's just, it's explicit. The groupings are explicit. And so we should get 353 rows. And what, 1, 2, 3, 4, 5 columns?
350.
The ones that say 0 was 0.0, because those were the ones that were blank values on the last screen when we still had 3. Or was it?
Because apparently this is treating null values as zeros.
Because they're not above 75 or grams.
This is true.
That's why I didn't have green sticky for a while. Just staring at that.
Okay. That's definitely a red sticky moment.
That was
I'm,
an empty sticky. I was trying to figure it out.
yeah, that's one of the things, I don't know. Because that's not right.
Yeah.
So what? So weight over 75. Let's get rid of this and see what happens.
It is the same. It just leaves it blank.
It just leaves them blank.
Yeah.
That's why I was trying to figure out how to get rid of the missing values or to exclude those, but it's interesting that it doesn't exclude it automatically.
Yeah, I think so. That is interesting. And this is the first time I've used this software, and so that may be a bug in the software that we need to report to the people who make this software, because that isn't really great. I guess though, like, in other words, like if you're trying to calculate averages, it won't count those, but it also might when you divide by the number of records that it returns. Yeah. So that is troubling. Let me look up, what and? Let's see, and so weight is not equal to, because if you have a space, it looks for a space, but then here, it's when it's null, because that kind of double quotes right next to it is this basically the same thing as null. Since this seems to be like really sloppy with this type checking, this software is, which is fun because we get to do interesting things like this, but it's also not great. 1000.0 to get the kilograms. So. And this is actually a good thing to sort of keep in mind, is that null values can trip you up and will trip you up. And so paying attention to those things is important, but there are ways generally to work around. So let's do another. So let's look at sort of starting to build up even more complex queries. So let's do select. Let's do everything from surveys, and there is tab completion in this as well. Even though it goes to lowercase, where year is greater than equal to 2000, and species ID, and then we're going to use a new keyword here, in, and we're going to give a list of DM, DO, or DS. And run. So that gives us what, 1,268 rows. So notice how generally the sort of process that we do is we start with something simple, and then we add more clauses one by one and sort of test their effects as we went along. And for complex queries, this is a really good strategy to make sure that you're getting what you want. And sometimes it can help to take a subset of the data that you're working on in a temporary database to practice the queries on if you're working on a really large data set. Just because on a really large data set, it might take seconds or minutes to run a complicated query. And when queries become more complex, it can be useful to add queries, to add comments, which you can do with tac. So we want to say we want to get all data after 2000 for demice. Demice species. These are stored in the surveys table. And then where year equals 2000, so we'll add a comment here, and then say something like, so demice species have the species ID, DM, DO, and DS. So you can add comments, and then this will run without even noticing that they're there. That's how comments work. And we're doing something really complicated, and these may help keep any collaborators, again, including yourself in 6 months, clear on what you were trying to do at the time. So we can also sort the results of our queries using order by. So first, let's actually go ahead and take a look at the species table. So we select everything from species. We get these 54 rows. That's a listing of all the species. And let's order it by taxa, which we use a new keyword here, order by taxa, and then ASC for ascending. So we can alternately use DESC to get descending order. If we don't put anything there, we get ascending order. So ascending is the default choice. So we can also sort on multiple fields at the same time. So now everyone's going to write a query that returns the year, the species ID, and the weight in kilograms from the surveys table, sorted with the largest weight at the top. So if you go to View, SQL log, or press Control L, everything that you've been putting in is stored. And if you scroll all the way up to the top, you'll even see all this is the stuff that actually created the tables. So when you create a table using the interface, it does that. All that's doing is like building an SQL query. Because all this stuff was developed when typing in queries was the only way to interact with these databases. That's an interesting thing going on. I'm going to have to play with that, but not now. So another note for sort of the order that we put things in, we don't have to display a column to sort by it. So we can select genus and species from species, and then where taxa equals bird, and then order by species ID. And so we can do this because sorting occurs before field selection. And so the computer does the where and filters the rows, and then it sorts the results, and then it displays the columns that we ask for. And so clauses are always written in this order. So we always have select, from, where, and then order by. It is possible to write queries as a single line. I mean, this will run just fine, but that's terrible because nobody can read it, which we'll probably be doing some of that in R anyway, putting things in as a single line. But this is easier to read when you're working in raw SQL like this. So let's combine what we've learned so far in a single query. So using the surveys table, let's display the 3 date fields, species ID, and weight in kilograms, rounded to 2 decimal places, for individuals captured in 1999, ordered alphabetically by the series ID. So those are kind of all the points that we need to hit for this. And take your sticky down. And when you got it, put the sticky up. Quick example to show a new way to do aggregation. We're not going to do this whole lesson because I want to get back into the R and show you how that works. So that's a little bit different. And we're going to be skipping over joins, which is a big topic that can get confusing. But y'all can look at that later. But mostly we don't need that for the R lesson. So I'm going to show this. So we can do aggregation functions in our select statement. So we can do select count, and this is an aggregation function. And then from surveys. So it ends up just giving us a single row that's the 35,549. So we can also get that count and then use another aggregation function so we can sum weight and get, what is that, 1,000,000 grams? 1,000,000 grams of rat. That's a lot of rat. And if we want to get that, say, in kilograms, we can run that sum through another function. Do that rounding function and get, I mean, that's a metric ton of rat. That's more than a metric ton of rat. And so there's other aggregate functions, and this is where you can get maximums of a sample, minimums, and averages out of that. We're not really going to do anything else with that right now. I actually am going to show joins real quick. I'm going to do one quick example of a join. So joins, we work with 2 tables. And the way that we do that is species.genus. And then comma, species.species. And then surveys.weight. And then we're doing this from surveys. And then we want to join that on species. And we need to use join on surveys.species ID equals species.species ID. So that tells on what variable, what row we're joining on each one, like what the relational, what the relation is between these two tables. That's why it's called a relational database. So now I have the weights of like each of these different types of rats with the weight, with the full genus and species name. And there's other joins, other ways to do it. There's a lot more that we could go into here. We're not going to right now. Instead, we're going to pull back up RStudio. There are distinctions between that, but that's really an advanced topic. Like that confuses professionals, and that depends on like how, like which direction you want the tables to go. I don't have good words to talk about it. Usually, like, and in some implementations, all there is a left join. So like Access SQL, you can't do a right join or an inner join. Those don't exist in that implementation. But some of it can do things where it ends up like getting like hundreds of thousands of records because of the way the joins work. If it joins on like multiple, like if it's not a unique key, especially, that can really sort of blow up on you fast. But that's really outside of the scope of what we teach. And so, and we may do, and if we have time, we'll do some more joins. But we're going to be using dbplyr. So we may want to check if we have it. Library dbplyr. And then also library RSQL Lite. Okay, I don't have that installed right now. Installed packages. It wasn't working because I was installing a package at the same time and it didn't want to change options at the same time. I don't blame it. That could have been, that could break everything. Is that better? Cool. And so far we've dealt with small data sets that can easily fit into your computer's memory. Like I think I have 4 gigabytes of RAM on this thing. And there are data sets that are bigger than that. There are data sets that are much bigger than that. Terabytes of data, especially, I mean, yeah, there's just terabytes of data. And so that's why SQL is really good, because it automatically will pull things off disk and search through that chunk and then pull through the next chunk and only put into memory what you actually want to see. And so that's why databases are a good thing. It's because as much as we would love to have infinite machines with no technical limitations, we actually have to do our work on real hardware. And so this is why storing the data outside of R and then organizing it into an SQL database is actually helpful. And so connecting to this database allows us to retrieve only the chunks that we need to do the current analysis. So that's kind of why I stopped there. So even better, many large data sets are already available in public or private databases, and you can query them without having to download all the data first, which is great because, again, some of those databases are multiple terabytes, and they're being added to all the time. And so instead of having to download a 5 terabyte data set every day in order to keep current, you can just query the little chunk that you're actually interested in, and then just rerun that one query that will only send maybe a few hundred megabytes over your connection on a given day. And so R can connect to almost any existing database. The most common database types have R packages that will allow you to connect to them. Like RSQLite, there's also RMySQL. RSQLite is really nice because it packages an SQL database into a single file. It's good for medium-sized stuff, but once you get into really big stuff, you really do need something like MySQL or the other options that I've mentioned a few times. Furthermore, the dplyr, the dataPlyr, the dplyr package, in conjunction with dbplyr, which is the database plyr, supports connecting to SQLite, MySQL, Postgres, as well as Google's BigQuery, and it can be extended, and there's some more information on that on the RStudio website. And so interfacing with databases using dplyr, it focuses on retrieving and analyzing data sets by generating select SQL statements, but it doesn't modify the database itself. It does not offer update or delete entries at all. So using dplyr, you cannot edit remote databases, which is kind of nice because you don't necessarily want to do that unless you're very sure you know what you're doing. And so we are going to demonstrate how to interact with the database using dplyr, using dplyr's verb syntax that we used earlier today, and also sending them raw SQL. And so the first thing we do is install these packages, and so we have that file, which I think it's over in SQLite, Portal Mammals SQLite. And I'm actually going to set my working directory. Over to the SQLite. And so then the first thing that we need to do is set up what's called the database connection. And I'm going to type this up in here. So we're going to call it mammals. And then we're going to use dbi. And this is some syntax I don't think we've seen yet. Then double colon, db connect, and then parentheses RSQLite, and then double colon, and then SQLite. And then you're going to want to point it to the Portal Mammals SQLite. And then that was actually an extra paren that I didn't want there. So you want to do the dbi double colon db connect, which is saying db connect is like a sub function of the dbi package, the database interface package. And then this in here, the first bit sets this up as like what type of database are we trying to connect to, and then what is the link to that. So the link I'm giving is a file that's in our same working directory, but this could be some HTTP on the other side of the planet that you're pulling this database connector from. This could be an IP address like 127.885.109.45 or whatever, and that's what you're connecting to. It depends. And so this, when we run this, this does not import any data. This is not a data frame. This is it's like a handle. It's or a socket that's or a door that you open to the database, and that's what the mammals represents here. And so let's actually take a look at the database. Let's do source DBI mammals. So if we look, we get source is Sqlite 3.22.0 and the location of where it's at. And then the tables tells us the tables that we have in that database. So it's like a spreadsheet with multiple worksheets. So let's do a basic query. So TBL, mammals, and then SQL, which says we're going to send an SQL statement. And then select year, species ID, plot ID from surveys. And run that. And so we get a return of a big old table. And so one of the strengths of dplyr is that the same operation can be done using dplyr's verbs instead of writing it in SQL. So you can write it in SQL, or we can do something like this. So surveys is table, mammals, and then surveys, which will just return the whole table. And then we do surveys, and then pipe into select, and then it's a year, species ID, and then plot ID. And so you can see that that returns the same result. So this here is, at least as far as the output is concerned, gives the equivalent output to this here. So whichever makes more sense to you, whichever is less of a pain in the ass to type in, whichever you happen to remember at the time, is what you can use. It doesn't really matter. And so in this case, the surveys object behaves like a data frame. And so we can also use any of the things that we use on data frames on it. So head, surveys, and then n equals 10. And so this output looks like a regular data frame. Table has 9 columns, and the head command shows the first 10 rows. So note that the columns plot type, taxa, genus, and species are missing from what we were doing before, but that's because these are now located in the tables, plots, and species, which we will do some joins here in our SQL in a moment. So there are some functions that don't work as we might expect. So in-row surveys. Gives us a null value. So R doesn't know. And if you scroll back up in the buffer a little bit, and you see that it says source lazy query, question mark by 9. And this is a key difference when you're using dplyr on data sets when it's in memory and those provided by a database. And to understand that, we'll take a bit of a closer look about how dplyr actually communicates with our SQLite database. So behind the scenes, and this is why these two things are equivalent, R actually translates your code into an SQL query, submits it to the database, and then translates that response into an R data frame. So these two things are doing the same thing to the database. So R never even sees the full survey table. The full survey table using these connections never has to come into R, never comes into memory. It's only what you ask SQL for. So let's do some simple database queries, similar to what we were doing before in SQL. So we do surveys, and then pipe that into, let's say, a filter where weight is greater than 5. We don't want the smallest. And then let's select.
Is it less than 5 or greater than 5?
Oh, I did want less than 5. We only want the little ones.
Okay.
And then we only want to select species, ID, sex, and weight. Sex and weight. And then run that. And so again, we get the lazy query that gives us the table. So it only gives us 10 rows here. And then it says, Bill, there's more. And so this is what Hadley has to say about it. When working with databases, dplyr tries to be as lazy as possible. It never pulls data into R unless you explicitly say, I want all this data. And it delays doing any work until the last possible moment and collects together everything you want to do and then sends that to the database in one step. And so it's trying to minimize hits on the database because generally people running databases do not like it when it's known as hammering their database. And it's can be interpreted as a hostile action in cyberspace. So when you construct a query, you can connect multiple verbs into a single pipeline, filter and select, and then so we want to take this and we actually want to say we actually want to save this data. So let's put this into data underscore subset. So now we have data subset. And let's take that data subset and let's pipe that into select, and let's remove that sex column. And so now all we have is species ID and weight. So this select command is not actually executed by R. This is sent to the database, and only this final result is retrieved and displayed. So even though this data subset is built off of this database connections that we have, we're not actually getting this final subset. When we run that command, it goes back and says, okay, now I need to build an SQL statement that will get me this information and then give that back to us. And we could always add more steps. We could filter by species ID or minimum weight, but that's why R doesn't retrieve the full set. It only retrieves the first 10 results from the database by default. And you may want to add an additional step and get the database to do more. And that's so we can sort of prototype until we figure out what we want to do with it. So to instruct R to stop being lazy and to retrieve all of the query results from the database, we need to add a collect command to the end of our pipe. So we have this data subset, filter by the weight less than 5, and then add another pipe here, and then actually collect this data. And now we have data subset, which is actually 17 observations of 3 different variables. So dplyr enables database queries across one or multiple database tables and using the same verbs that we encountered before. So we can use the same commands whether you're working with a remote database or a local data set. And so this sort of stuff is nice so that you don't have to necessarily have to think about SQL if you don't want to. If this stuff makes more sense, use it. But also, being able to use SQL queries directly is really nice, because if someone you're working with who's an SQL whiz puts together a query that gets the results you need, all you have to do is paste it in using one of these, and then you're good to go. And so being able to like interoperate with whatever you can only sort of increases the amount of people and tools that you're able to work with. And so we're going to illustrate some joins and these more complex queries. So we're going to make a new hookup here. We're going to do plots, and let's do alt, and then table, and then mammals, and then plots. And then I'm going to go and run that too. And so now we get another one of these responses that has the plot ID and the plot type. So because we have that relation between the plot ID in the surveys table and the plot ID in this, let's go ahead and do some joins on that. So we can see here like kind of how these inner and left joins work. So we have 2 tables. We have table X and table Y. And we want to do an inner join of table X onto table Y. And so what we do is we get the IDs that, these IDs are the corresponding values. They're the relatable values. And so we end up getting 2 and 3, which is south and east, and then we also get 1.2 and 3.3. Which seems kind of odd. But it really just clips the tables, right? And then for a left join, which this is the more common kind of join that I've seen used. I haven't, like, in the wild and even in code snippets, like what people normally do with this kind of stuff, is this kind of left join, which we get the IDs of 1, 2, 3, north, south, east, and then we see that we have, okay, no, we have 2 and 3 in this table as well, and we have some data on those IDs that will relate to this plot information. So how does that actually look? How can we actually use that in code? So let's see, plots, and then a pipe, and then we do a filter on plot ID equals 1, and then put that through another pipe, and then do an inner join, surveys, and then another pipe, and let's go ahead and collect that. And then run that. So what this did is extracted all of the surveys from plot 1. And also gives us the information about what plot type it is in the same table. Which just maybe if there's something we want to print out and print this out and give this list to somebody. Because even though we do everything on computers, not everyone does. So don't forget that you need this collect, because if you don't use that, all you get is the first 10. So basically, without using collect, it's always head 10. And so this is kind of your final exam, which we kind of did joins quickly. So you may need help, work together, ask questions, cheat as much as you can. Is to write a query that returns the number of rodents observed in each plot in each year. And we're going to want to connect to the species table and then write a query that joins the species and survey tables together to exclude all non-rodents. And the query should return counts of rodents by each year. And you can also, if you're feeling like hot stuff, write a query in SQL that will do the same thing. And you can join, and here's the SQL join syntax. It's kind of a hint.